We've been measuring the biggest planet wrong, and the truth just got revealed. For over 400 years, humanity believed we had Jupiter's measurements locked down. We drew the maps, calculated its circumference, and taught generations the same numbers. Jupiter was the undisputed king of the solar system, the giant we thought we fully understood. But in February 2026, NASA's Juno mission delivered news that shocked the entire planetary science community. Jupiter is shrinking. Not dramatically, but measurably. Its equatorial diameter is 8 kilometers smaller than every previous model predicted, and it is 24 kilometers flatter at the poles. On a planet with a diameter of 143,000 kilometers, these numbers seem small. Yet they are forcing scientists to rewrite decades of models about how gas giants form, how their interiors work, and what we assume about thousands of exoplanets orbiting distant stars. This is the story of Jupiter, the planet that's shrinking, and why it changes everything. Jupiter is not just big, it is overwhelmingly dominant. If you took every other planet in our solar system and combined their mass into one object, Jupiter would still be 2.5 times more massive. It contains more mass than all the other planets put together. Its famous Great Red Spot is large enough to swallow Earth entirely and still have room left over. The planet spins so fast, completing one rotation in less than 10 hours, that its equator bulges noticeably due to centrifugal force. Jupiter has at least 95 confirmed moons, with more being discovered every few years. 4 of these moons, Io, Europa, Ganymede, and Callisto, are so large they would qualify as planets if they orbited the Sun directly. Ganymede is actually bigger than the planet Mercury. These moons create a miniature solar system around Jupiter, each with its own unique geology and mysteries. Beyond its size and moons, Jupiter has played a critical role in shaping our solar system. During the chaotic early years, when the planets were still forming, Jupiter acted as a massive gravitational shield. Its enormous pull flung dangerous asteroids and comets outward, away from the inner solar system. Without this protective influence, Earth might have suffered so many catastrophic impacts that complex life would never have had the chance to develop. In a very real sense, our existence here today depends on Jupiter's presence as the solar system's cosmic bouncer. For centuries, astronomers observed Jupiter through telescopes and believed its shape was well understood. They measured its rapid rotation, watched the colorful bands of clouds racing at speeds over 600 kilometers per hour, and mapped its magnetic field, which is 20,000 times stronger than Earth's. Everything appeared consistent with long-standing models. Then Juno changed the game. Juno arrived at Jupiter in 2016 and has been orbiting ever since, skimming just a few thousand kilometers above the cloud tops. Its instruments have collected precise gravity data, magnetic readings, and atmospheric measurements far more accurate than anything before. After years of analysis, the February 2026 announcement revealed the surprising truth. Jupiter's shape is more oblate, more squashed, and slightly more compact than previously thought. This is not a minor correction. A planet's shape is intimately connected to how its mass is distributed from the core outward, how fast it rotates, and how its deep atmosphere interacts with the interior. Even small changes in measured shape reveal enormous details about what is happening thousands of kilometers beneath the visible clouds. If our old measurements were wrong, then our entire understanding of how Jupiter formed 4.5 billion years ago must be adjusted. And if Jupiter's formation story needs rewriting, then the timeline of how our entire solar system assembled itself needs careful re-examination. This revelation opens the door to deeper questions. What does the new data tell us about Jupiter's hidden interior? How does this affect our view of its violent weather systems? And what does it mean for the search for life elsewhere in the solar system? The answers are more surprising than most people realize, and they begin with the wild, chaotic atmosphere that defines Jupiter's personality. Jupiter does not have a solid surface like Earth. Instead, its outer layers are a thick, turbulent ocean of gas that gradually becomes denser and denser with depth. What we see from space is the top of a massive, ever-changing weather system powered by heat from the planet's interior and its rapid rotation. This combination creates some of the most extreme atmospheric phenomena in the entire solar system. The most famous feature is the Great Red Spot. This enormous anticyclonic storm has been raging continuously for at least 350 years. First observed in detail in the 17th century, it is still going strong today. Even now, after shrinking somewhat over recent decades, it remains larger than our entire planet. The storm rotates counterclockwise once every 6 days, with wind speeds reaching 430 kilometers per hour at its edges. Scientists still debate exactly why it has lasted so long, while similar storms on Earth dissipate in days or weeks. The latest Juno data suggests that the Great Red Spot may be anchored much deeper in the atmosphere than previously believed, possibly extending hundreds of kilometers downward, where it taps into Jupiter's internal heat. Jupiter's atmosphere is divided into dozens of alternating light and dark bands known as zones and belts. These bands circle the planet at different speeds, creating massive wind shears. In the zones, lighter-colored ammonia clouds rise upward, while in the darker belts, material sinks. This creates a global conveyor belt of weather that has been operating for billions of years. Winds in some jet streams exceed 600 kilometers per hour, faster than the speed of sound on Earth. Even more extraordinary is the lightning activity. Jupiter's lightning is not just more frequent than Earth's, it is dramatically more powerful. Bolts on Jupiter can release energy up to 100 times greater than typical terrestrial lightning. Juno's instruments have recorded flashes occurring deep in the atmosphere, sometimes originating from water clouds located more than 100 kilometers below the visible ammonia cloud deck. These storms are so intense that they create radio bursts detectable from Earth. Perhaps the strangest phenomenon uncovered by Juno involves mushballs. As dramatic as the visible atmosphere is, the real revolution lies even deeper, thousands of kilometers below the clouds, where pressures become unimaginable and hydrogen begins to behave like a metal. Jupiter's interior is divided into distinct layers, but unlike rocky planets, these layers blend gradually into one another. The transition starts just a few hundred kilometers below the cloud tops. Here, the pressure rises so rapidly that the hydrogen gas is squeezed into a supercritical fluid state, neither fully gas nor liquid. As you descend further, the pressure reaches millions of times Earth's sea level pressure. At around 10,000 to 20,000 kilometers deep, something extraordinary happens. The hydrogen atoms are crushed so tightly that their electrons break free and flow freely. This creates metallic hydrogen, a substance that acts like an excellent electrical conductor, similar to copper or silver, but on a planetary scale. This metallic hydrogen layer is what generates Jupiter's enormous magnetic field, the strongest of any planet in the solar system. The field is 20,000 times more powerful than Earth's and stretches millions of kilometers into space, creating a magnetosphere so vast it can sometimes be seen from Earth as faint auroras on the planet's poles. The 2026 Juno data showing a more oblate shape suggests that this metallic hydrogen region may be distributed differently than older models assumed, possibly with more complex flows and currents that affect the planet's overall moment of inertia. Deeper still lies the core, or what scientists now call Jupiter's fuzzy core. For decades, models assumed Jupiter had a dense, rocky or icy core about 10 to 15 Earth masses, concentrated in a relatively small region. The new Juno gravity measurements have overturned this idea. Instead of a sharp, compact core, Jupiter appears to have a diluted, extended core that blends gradually into the metallic hydrogen layer above it. This fuzzy core may stretch across a region up to half the planet's radius, with heavy elements like rock and ice mixed throughout rather than neatly settled at the center. This discovery is directly connected to the shrinking revelation. A more diffuse core changes how mass is distributed inside the planet, which in turn affects how the whole world bulges at the equator and flattens at the poles under its rapid rotation. The 8-kilometer equatorial reduction and 24-kilometer extrapolar flattening make much more sense with this fuzzy, extended core model. It implies that during Jupiter's formation, it did not fully separate its heavy materials from lighter hydrogen and helium as cleanly as we once believed. Scientists now think Jupiter may have formed through a process called pebble accretion, or experienced late-stage giant impacts that stirred up its interior. Some models even suggest Jupiter once had a much denser core that was partially eroded or diluted over time by convective mixing. These possibilities are rewriting the timeline of the early solar system. If Jupiter's core is fuzzy and extended, it means the planet accreted its mass more quickly and violently than previously modeled, potentially disrupting the formation of nearby planets like Saturn or influencing the delivery of water to the inner solar system. The implications reach far beyond our own neighborhood. Thousands of exoplanets discovered by telescopes like Kepler and TESS are gas giants similar to Jupiter. Many of these hot Jupiters orbit extremely close to their stars. If our understanding of Jupiter's interior was flawed, then our models for how all these alien worlds formed, evolved, and migrated must also be updated. A fuzzy core model suggests that gas giants can have more varied internal structures than we assumed, affecting everything from their magnetic fields to their atmospheric compositions, and even their potential to host habitable moons. This deeper understanding of Jupiter's interior also helps explain its incredible heat output. Even though it is far from the Sun, Jupiter radiates almost twice as much heat energy as it receives from sunlight. This leftover heat from formation, combined with helium rain falling through the metallic hydrogen layer, drives the powerful convection that fuels the storms we see on the surface. The shrinking measurements from Juno give scientists a new way to calculate exactly how much heat is still trapped inside and how it moves outward. The more we peer beneath the clouds, the clearer it becomes that Jupiter is not a static ball of gas, but a dynamic, evolving world, still slowly adjusting to its formation billions of years ago. Jupiter is not a static ball of gas, but a dynamic, evolving world, still slowly adjusting to its formation billions of years ago. This new understanding forces us to reconsider everything we thought we knew about how our solar system came together. The shrinking measurements and fuzzy core discovery have major consequences for planetary formation theories. For a long time, scientists followed the core accretion model. A solid core forms first, then gathers gas. But Juno's data suggests Jupiter formed much faster and more turbulently. Missions like the James Webb Space Telescope are already studying exoplanet atmospheres. The updated Jupiter reference model will help scientists decode what they see more accurately. On a broader scale, the shrinking Jupiter revelation highlights how little we still know about giant planets. It reminds us that even the most studied objects in our cosmic backyard can surprise us. Every small adjustment in Jupiter's measured shape ripples outward into cosmology, star formation theories, and our search for Earth-like worlds. If Jupiter's interior is more disordered than we thought, then the conditions required for life-bearing planets might be more common or more rare than previous calculations suggested.